So we're going to be talking more about atoms. We don't have any atoms in this class this time, do we? So you guys did a great job of telling me, like, there's a nucleus, right? And do you remember what's in the nucleus? Two things are nucleus. Protons and neutrons, exactly, in the nucleus. What's outside the nucleus? Electrons, exactly. So kind of what you're describing is basically in 1913, we kind of knew that, basically. But I want to tell you, historically, what we used to think about an atom. It has to start somewhere, right? Okay, so clear back in 1803, Dalton, who was colorblind, kind of an interesting young man, but he basically came up with this concept of an atom. And it wasn't, the Greeks before him had talked about what an atom is. But basically he says, oh, all matter, it's made up of little pieces. You can't see the little pieces, but little pieces. So this concept of an atom. Notice he didn't know anything about the nucleus or protons or neutrons or electrons. Then in clear, that's a long time, like 100 years later, 100 years after that. We're like, okay, atoms are great, but atoms actually have kind of different pieces in them. Okay? And so if you read your textbook, they'll talk about this. I think this was the one with the, no, that's the Rutherford. But it'll talk about how Thomson actually said, you know, there are entities in those atoms that are positively charged and negatively charged. We kind of call this the plum pudding model. How many people have eaten plum pudding? Plum pudding? Okay. But it's just kind of a mixture. Don't know about the nucleus yet. Okay, Rutherford came up with the concept of a nucleus finally. Okay, so 7 years later. Faster and faster. Okay, he did the thing with the gold, with a thin gold foil, and basically sent a beam of energy, and every once in a while that energy would hit a nucleus, a center of an atom, and it would come ricocheting back. Otherwise, it basically went through because it's going through this electron cloud. I just think that's amazing. Atoms are mostly empty space. The dude who kind of, and I saw this on Neil deGrasse Tyson's Cosmos episode, and he basically said the dude who finally figured out that atoms are basically a hard nucleus with an electron in a cloud outside. It's empty space. Atoms are mostly empty space. He was scared to get up in the morning because he was yeah. Okay. So one of the things we're going to talk about later is that electrons are not all created equal. So what Bohr did was said, oh yeah, you got electrons out there, and oh yeah, they're negatively charged, and oh yeah, you have a nucleus. Rutherford came up with that. In the nucleus, you have the positive pieces, protons, and you have neutrons in the nucleus. But what Bohr said is those electrons out there are kind of organized, okay, into these different energy levels. Okay, that's what Bohr said. And then Schrodinger, he kind of built on what Bohr said. So actually it ends with basically the Schrodinger model. And I mentioned Heisenberg's uncertainty principle the other day. Basically, you cannot know the location, and both the location and the energy of an electron around an atom at any given time. You can't know both of those things. It's uncertain. Okay. So basically, these kind of this is representing kind of the cloud. So that's kind of what we know about an atom. So back in, was it 1803, right? Dalton came up with and to me, he kind of just brought it up again, the concept that all matter is made up of atoms. Okay. Was it Aristarchus, maybe? Some Greek dude a long time ago. Okay. So now the way you read this is the blue part is not entirely right. The blue part is I don't know if anybody's in here colorblind, let me know if you are, but after class if you want. But the blue was part of his original Dalton's atomic theory about atoms, but it's wrong. What's wrong about it?
Yeah, we split the atom.
We can split the atom, exactly. Yeah, he said those little atoms, you're not breaking down any further, and we know we can, yeah.
Let's smack them together.
We usually call that extraordinary means, by a type of chemistry called nuclear chemistry. Okay. All right, there's something blue here, too. Okay. You're like, well, why show me something that's not right? Well, it's historical, okay? And a lot of it's black, which means he got it right. I love science, and you know, just, it doesn't have to be like physical science, you know, it could be the social sciences. I love the fact that we don't have to reinvent the wheel. We build on what somebody else has thrown out there. So he said, all right, we got these pieces of matter called atoms, and he said that if the atoms are the same element, he said that they are going to have the same chemical properties. That's awesome. But he said that if two atoms are the same element, they will weigh the same. That is not true. As some of you know, it starts with the letter I, isotopes. We're going to talk about different elements have different, actually the reason that makes them weigh different is because they have different neutrons in their center. That's it. Neutrons make them way different, but they're the same element. Okay, so that's okay. Then, this is pretty cool. So not only did Dalton, I'm just thinking about this now, not only did he understand the concept of a matter is made up of little pieces called atoms, but he said that atoms can join together to make repeating units we call molecules and formula units, okay? Make compounds. We write a formula of a compound. The thing that's not right here is that they will be in whole numbers, but they aren't necessarily small. If you've done much with biology, you know when it comes time to say the number of carbons, hydrogens, nitrogens, oxygens, and maybe sulfurs that are in like maybe a DNA strand, okay, they are large. Okay, if you distill it down to, you know how we write H2O?
It's a ridiculous number.
Yeah, you're like, all right, 2 hydrogens and 1 oxygen, right? Okay, but if you were to distill down just a single strand of DNA, you know, and I don't know what else it has in it, but I know it has these things in it. You have big numbers here. Okay, so that's just it. The last one, I've got red here instead of blue. Okay, the red is actually to go ahead and correct him. And actually, this last statement is kind of similar to his first statement, which was incorrect. Okay, it is true to say, Dalton said that atoms can't be created or destroyed. Okay, but if you go ahead and amend what he said with saying they can't be created or destroyed during ordinary chemical reactions, then you basically have made his statement correct. And it goes back to what y'all said, we can do nuclear reactions. Okay, nuclear, maybe you guys already know this, but nuclear fission breaks an atom, and nuclear fusion combines atoms. Yeah.
Cold fusion.
So one of the things that I just think is awesome about our universe is there's all sorts of things that are conserved. If you're like a numbers person and like to track the flow of things, okay, it just doesn't disappear. It goes somewhere. Okay, so there's the conservation of energy. There's the conservation of matter, and is written here. So if we think about the conservation of matter, we could say that atoms are conserved, okay? Matter itself is conserved. Mass is always tracked, okay? Mass is conserved. Again, we know, according to Einstein, that mass can be converted into energy, okay, according to E is equal to mc squared. But again, that's back to nuclear reaction. All right, so let's take a look at these. These are pretty good. 27, 28. Maybe.
And these will be due on a Friday or?
Yes, these will be due Friday.
Wait, I'm not coming here on Saturday.
They're due on Saturday.
Yeah, so 27, they're about Dalton's atomic theory. So, you know, feel free to just use my notes or look a little bit further in read your textbook. But basically, which of these are not consistent, are inconsistent with Dalton's atomic theory? Okay. That's 27. The answer's in the back of the book. 28 is which are consistent. Okay? No calculator required. Okay, so let's do a few more slides. Get down the road. So it was after Dalton that came Thompson's model, and I mentioned the plum pudding model. Basically, they thought it was a homogeneous mixture. Each atom just had positive and negative charges, but they were all kind of mixed together. Then the next few slides. This one finally is what I told you the other day. Is if you're to take a BB, if you read this, the captions, it says this is a BB. And it says basically a 10-story building. Okay, and if you figure a story is, I don't know, if you go 10 foot, then that would put you at 50 feet. Okay, so put your BB there, go 50 feet away. So like, okay, so if you're on a football field, how many yards is that? 50? 300 yards.
100 yards, 300 feet.
Okay. Far, far away. And so the dude who was afraid to like stand up on his floor was right to be afraid. I know. It's amazing. So I have a slide on each one of these, and so again, for your Unit 2 exam, I'm going to test you over this stuff. No calculators required. I'm going to kind of ask you some characteristics about these three. They're called subatomic, like smaller than an atom, subatomic particles. Okay? And some of the stuff you definitely already know. So just embrace that. I already know that. But don't tune out. Okay. So one of the things we already talked about on Monday was kind of the how an atom is assembled. So we said in the center is a nucleus, and the two colors there mean the two particles, the neutrons and the protons in the nucleus, and then the electrons in a cloud outside the nucleus. So I was looking at this at my office. This is amazing. So if you have to read the caption kind of. So it says atoms are small. We've got that. Okay. It said if you take a pebble, okay, and if every atom inside a single pebble were the size of the pebble itself, which is kind of weird. Pebbles are small. They have a lot of atoms in them. Go ahead and basically giant size each atom inside a pebble to the size of the pebble. It's kind of strange. Then you are looking at basically larger than, I don't know what size of pebble they have, but basically those atoms that were giganticized, okay, to the size of a pebble, within a pebble, would basically be the volume of Mount Everest.
Pebbleception.
Yes.
Inception with a pebble.
It is. So protons are positively charged. They're the happy piece. Okay. They are found in the nucleus. Again, things we've already been talking about. One of the things you may already have a sense of is that when it comes time for those three pieces to go ahead and be attracted to each other, it's going to be the protons and the electrons. They are attracted to each other. But guess what? What do you think about a proton and a proton? It wants to repel each other. Okay. So protons in the nucleus help keep electrons in line. Okay. So of those three particles, and I'll try to emphasize this, there'll be other ways to kind of think about it, but in fact, I'm not sure, I haven't decided which lab we're going to do tomorrow. We might do one that kind of dives into a little bit kind of what's in an atom. But what gives them weight, because we said you can have two atoms of the same element, but they weigh differently. What did I say is different about them? Which piece? The neutrons. The neutrons are different, exactly. So the thing that gives any atom mass is neutrons and protons. Electrons, not so much. Okay. So what's in the nucleus gives it weight. All right, so I like this one. So when it comes to knowing say you get an atom. You're like, I don't know what element it is. Well, when it comes to identifying what element an atom is, all somebody has to do is tell you the number of protons in the nucleus. And then what you do is you have a periodic table. Remember, you'll never be without a periodic table in here. You look at the whole number, and remember, I think I might have told you that for every decent periodic table, there's always a whole number, and that whole number is the number of protons in the nucleus. So that's why we say protons actually define what an atom is. So we talked about nuclear fusion. Basically, you can take a hydrogen, and the sun does this all the time, and squish them together under great temperature and pressure. And then basically, by the way, hydrogen, how many protons are in a hydrogen atom? 1. Yep, it's atomic number 1. It's got 1 proton. So you squish them together. Now we have something with 2 protons. So what element is this new atom? It's helium. Yep. Exactly. All you got to do is change the number of protons. It's hard to do. You know, when they were doing that, the alchemists were basically trying to change what element something was from one metal to another metal. Well, they would have had to change the number of protons in the center. Okay, so neutrons, like Switzerland, they have no charge. Neutrons are found in the center of an atom called the nucleus. So we have protons and neutrons in there. Electrons don't get to come in. And this third one is, remember I said that protons will repel other protons, okay? And electrons will repel other electrons. So it's actually, when we look at the nucleus, thank goodness that the neutrons are in there to help kind of dilute this repulsion between fellow protons. So the neutrons kind of help them get along, kind of give them a little bit of space. And this one's kind of like the last one, that if anybody ever asks you, yeah, you know an atom weighs something, but atoms weigh something only kind of because of what's in their nucleus. You know, electrons do not weigh much at all. What's in their nucleus are their protons and their neutrons. Yep. The electron has all the volume. Speaking of, electrons are negatively charged. So electrons are found, and I think it might be coming up, but they're found outside the nucleus. They're actually found in what we call a cloud outside the nucleus. Kind of like you saw Schrodinger's model, a cloud. So electrons are found outside the nucleus. So electrons are really light, even if you have a lot of them. They're very light. They don't bring much mass, but they basically give you the volume of an atom. We kind of visited that with the BB having this volume versus a 10-story building. And the last one, there's more things, but I think this might be the last one I have up here, is that when we go to talk about compounds, like water is an example of a molecule that's the compound H2O. When we come to sticking those 3 atoms together to making that water molecule, it's going to be the electrons that reach out. Well, I guess that's not saying it right. The electrons don't necessarily reach out, but it's going to be the electrons that actually kind of drive those 3 atoms connecting together. Okay. Well, we will pick up here on Friday. Yeah.
Time to go already?
I know. You're fun, Cameron.